In this video, I'm going to work through the solutions to the homework from week 2. So the first question, we're trying to prove a logical equivalence using a series of logical equivalences. So you'll want to have that table of logical equivalences or that document with all logical equivalences that we'll use in this problem. So make sure to follow along with that. Okay, to get started, we need to pick one side. So we'll either start on the left-hand side or the right-hand side. And it doesn't matter, you can start on either side, but I'm just going to go ahead and start on the left-hand side. If I start with negation of P implies Q implies R. So the first logical equivalence I'm going to use is that the implication is logically equivalent to not P or Q. So I'm going to replace all the implications that I see with the negation of the hypothesis or the conclusion. So with this implication here, I'm going to negate my hypothesis, which is not P, or my conclusion, which is Q implies R. And then I'm going to apply this one more time with the Q implies R. So I'll have the negation of P, or negation of hypothesis or conclusion. So I'm using this equivalence here. P implies Q is logically equivalent to the negation of P or R. So here's my justification. And on the left-hand side are the actual steps that I'm taking. So when you're working through this, you want to keep in mind where you want to go. And I noticed that I've got Q implies something. So it'd be nice to have negation of Q or P or R. So I want to work towards that. Here I see a double negation, so I'm going to go ahead and fix that. Negation of P is just P. So I have P or not Q or R. Now I have all ors, so I can go ahead and write this in any order that I want. So if I've got P or Q or R, because or is associative, I can write this as P or Q or R. So I will write this as P or not Q or R. And so I know I want to have not Q in front, so I'm going to use the commutative property of the or operator to change this order. So P or Q is logically equivalent to P or Q or P. From the associative law, this is logically equivalent to this. So P or Q or R is logically equivalent to P or Q or R. And then I have the negation of something or a conclusion, so I can write Q implies P or R, because P or not P or Q is logically equivalent to P implies Q. And now I've gotten to the right-hand side exactly. Okay, now we're trying to show that this particular implication is a tautology. So I'm going to go ahead and rewrite this implication as not the hypothesis or the conclusion, because it's a good place to start to try to get all ands and ors. So the first thing I'm going to use is P implies Q is logically equivalent to not P or Q. So not the hypothesis or the conclusion. Okay. So then I'm going to use De Morgan's laws. If I negate two propositions joined by and, it becomes the negation of both propositions with an or in between. So I've got negation of P or negation of Q or P or Q. Now I've got all ors, so I can do these in any order that I want, or combine these in any order that I'd like. And I see a not P and also a P, and I see a not Q and a Q. If I join those together, I know that P or not P is true. So I am on the road to showing this statement is always true. Let's go ahead and use the associative law here. Or let's use commutative first. So I'm going to rewrite the order. So I'm using the fact that P or Q is logically equivalent to Q or P. And then I'm going to use the show associative law. I can group so I'm going to go ahead and group that P with that first disjunction there. Well, then I'll use associative law again to get negation of Q or not P or P. And then I can use the property that P or not P is always true. So not Q or true or Q. And if I have P or true, that's always true. So associative law allows me to group these first two, and that gives me true or Q. And applying this property again, I get true. All right, now number 3. I'm going to start on the left-hand side because it looks messier, which might be helpful, maybe not. So I'm going to start with negation of Q, and P implies not Q, implies not P. Okay, so I'm going to start by, I like this implication, so I might leave this one in there, but I'm going to go ahead and write the innermost implication as an and, negation of hypothesis or conclusion. Negation, hypothesis, or conclusion. And all this implies negation of P. Now let's just double check here on the absorption laws. I want to verify that I've got these. So I've got something on the outside of an and the inside of that or. So this is on page 27 if you've got the 7th edition of the text. So the absorption law says P and P or Q is logically equivalent to P. Now this makes our work a lot easier because at this point you could distribute the not Q and, but you don't have to. We can make it easier because I've got this not Q here and the not Q on the inside, so that tells me that I'm just going to end up with not Q here based on the absorption law. Absorption. And this is on page 27 of the text. And now we're almost done. And like I said, you can do this a different way. You could go ahead and distribute that, but obviously, as you can see here, this is easier. This is a contrapositive, so I know that this is logically equivalent. I know that negation of Q implies negation of P is logically equivalent to its contrapositive. And we're done. All right, so now we're moving into predicates and quantifiers. So we want to take these quantifiers and predicates and try to represent these statements in English. So if you notice, they look really similar, but we've got the variables in a different order. So it'll be important to note that that order of those variables is important and the order of the quantifiers is important. So I'm going to read this just bit by bit and not really do any translation right now. I'm just going to say for all Y, and now Y is classes. So for all computer science courses, there exists, now X is student, there exists a student taking that course. So this tells me so this is saying pick any computer science course. There's a student in that course. So there's a student in every course. Every course is being taken by at least one student. That's better. Every course is being taken by at least one student. So that's a nice translation. I think that's a little bit more clear than the previous one. For all students, there exists a course they're taking. Student is taking. So now let's try to think about a little bit more clear way of interpreting this. So for all students, there exists a course that they are taking. So this means that if I pick any student, that student will be taking a course. For all students, there exists a course the student is taking. So I can say every student is taking a computer science course. Every student in the class, notice that, so let's say that. Every student in the class is taking a computer science course. So hopefully that's a little bit more clear there. Every student in the class is taking a computer science course. Every course is being taken by at least one student. Okay, so for all x, p of x, now we're writing out these quantifiers and predicates in terms of our domain containing 3 elements. So if p of x is true for all elements in our domain, then it must be true for 0, and it must be true for 1, and it must be true for 2. If we're thinking about there exist, this means it only has to be true for one of them. So that makes me think of or. So or is true when one or more pieces joined by or is true. Okay, so on number 7, we are given kind of an abstract predicate with no specific meaning, but we're given specific truth values for some inputs. And for each input, we could either put in 1, 2, or 3 for x and y, and then we evaluate the truth value. So let's go ahead and write out all our possible combinations here. We have p of 1, 1, p of 1, 2, p of 1, 3. We could have p of 2, 1. We could have p of 2, 2. We could have p of 2, 3. And notice that the order of these inputs matters. So p of 2, 1 is not necessarily the same as p of 1, 2. So be careful, we've got to list all these separately. So we have 9 possible truth values here, or 9 possible inputs. And our truth value will either be true or false. So p of 1, 1 must be false because it's not listed. True predicates here. So p of 1, 2 is false. P of 1, 3 is true. P of 2, 1 is true. P of 2, 2 is true. P of 2, 3 must be false because it's not listed. P of 3, 1 must be true because it is listed. P of 3, 2 is true. P of 3, 3 must be false because it's not listed. So A says, for all x, for all y, p of x, y is true. So this means that if I pick any x and y, that p of x must be true. So I know this is false because I have some true and some false. So my counterexample, p, let's just see, p of 1, 2 is false. So I only need one x value and y value to show that this is a false statement. Now let's look at B. This says there exists an x for all y for all y such that p of xy is true. So this tells me that I should be able to pick one x, and if I loop through all the y's, it'll make p of xy true. But if I check one, let's check one. Because p of 1, 1 is false, we know that that doesn't work. I could check 2, but p of 2, 3 is false, so I know that doesn't work for an x. I could check 3, but p of 3, 3 is false, so this is not true. Now, if p of 3, 3 were true, actually this would be a true statement, because we'd say x is that y that exists such that any y that I plug in, I get a true predicate. So this is false, and your justification is just these 3 false predicates. Okay? This is saying for all x, there exists a y such that p of xy. So this is saying for any x that I choose, I can find a y that makes p of xy true. And this is true, right? If x is equal to 1, y equals 3 makes it true. P of 1, 3 is true. And if x is 2, then y of 1, it makes it true. So p of 2, 1 is true. And if x equals 3 and y equals 1, p of 3, 1 is true. So for every x, I found a y. And now it doesn't have to be the same for all x, right, because of that order. And saying pick that x, then pick that y. So this is true. All right, now we're negating these statements involving quantifiers and different connectives. So we want to understand a couple things. If I negate a there exists, it becomes a for all. So these are just De Morgan's laws with predicates. If I negate a for all, it becomes a there exists. And also, let's see what we'll need here. If I negate 2 statements joined by or, De Morgan's law, and looks like I'll also need the negation of P implies Q is P and not Q. Yeah, so if I negate there exists X, F of X implies A of X. So if I negate a there exists, it becomes a for all. Negation of F of X implies A of X. So I want that negation to be right in front of the predicate. So right now it's outside of it. I want it to be in front of F, in front of A. So I'm going to use this equivalence to write it that way. So I'll have F of X. So hypothesis and negation of conclusion. If I negate a for all, it becomes a there exists. And if I negate an or, 2 statements joined by or, becomes an and by De Morgan's laws. So I've got there exists X, negation of F of X, or A of X. And then if I negate, using De Morgan's law here, there exists X such that negation of F of X, negation of F of X, and negation of A of X is there exists X, double negation, and negation of A of X. If I negate 2 statements joined by and, we will change our connective to an or and put that negation out in front of each piece. Negation, or, negation, Now if we negate there exists, it becomes a for all. If we negate a for all, it becomes a there exists. And we have one more push through with that negation for all x. So now we've got some statements involving quantifiers, and we're trying to figure out if they're true or false. Part A, I've got for all x, for all y. So any x and y that I choose, this implication must be true. So if I'm trying to find a counterexample, because I'm given that information, I want to know, is there a situation where my hypothesis is true but my conclusion is false? So when I think about two integers squared being equivalent but not equal, I think of x equals a positive and the negation of that, because x squared will be 1, y squared will be 1, but x is not equal to y. So this is a situation where the hypothesis is true, but the conclusion is false. So this is a counterexample. X equals 1, y equals -1. We could do that. We could do x equals -7 and y equals 7.